Hello everybody and welcome to Scalar's YouTube channel. This is Mahima Hans and I'm a software engineer and a mentor. And this is part 2 of our dynamic programming series. In part 1, we discussed the basics of dynamic programming and solved a few basic problems. And today we'll be solving some easy and medium level problems of dynamic programming from LeetCode. But before we get on with the video, make sure to check out Scalar's free masterclasses by industry leading experts only on Scalar's events page. The link is in the description. So let's get started. So first let's discuss the problem climbing stairs. It's a very easy problem on LeetCode and we're starting with a few easy problems first before we move on to medium difficulty level problems. So let's read it and try to understand what we're trying to do. So you're climbing a staircase and it takes n steps to reach the top. And each time you can either climb 1 or 2 steps. So at the end we have to find out how many distinct ways are there by which we can climb to the top. So let's say to explain it better on paper, let's say we have n equal to 2. So n equal to 2 means we have to reach the second step. So if we start from the bottom, either we take one step and then another step, this is one way, or we can take 2 steps from the 0th step, like from the ground itself. So if we take 2 steps, that's another way. So there's only 2 ways because at every point of time we can either take 1 step or we can take 2 steps. So the number of ways to reach the top here is 2. If we check for n equal to 3, there are 3 stairs. So we start with 1 step. Then we can take either 1 step or we can take 2 steps. So it's like this or like this. And here we have to take one another step. There's also a possibility where we can take 2 steps initially and then 1 step. So there's only these 3 ways using which we can climb to the top if there are 3 stairs. So now we have to find the number of ways we can reach to the top for any generic n value. We were able to do this manually for n equal to 2 and n equal to 3 because these were pretty small values and it was easy to find. But here we are aiming to find it programmatically. So if you observe in this particular example or in this particular problem, we can either take 1 step or we can take 2 steps. So the number of ways that are there to reach the top would be the summation of the number of ways that are there if we start with 1 step plus the number of ways that are there if we start with 2 steps. So let's say we are standing at this ground at the stair 0. So we either take 1 step and we reach 1 or we take 2 steps and we reach 2. The answer would be the sum of the ways that would come from this chart, this point, like when we are going from 1 forward, and the number of ways that would come from this path. So let's do it further. Let's create our chart further for n equal to 3. Then when we are at the first stair, then again we can either take 1 step or we can take 2 steps. So if we take 1 step, we reach second stair. If we take 2 steps, we reach the third stair. So this is one answer. We've already reached our top of the stairs, so this is one answer, and from here we'll return 1. So this path has given us one answer. It will return to the to this stair and we'll return it to the final 0. Then from this path we've reached 2. There is again 2 ways. Either we take 1 step, we reach 3, or we take 2 steps, we reach 4. If we take 2 steps, it's out of the out of bounds, or we can say our array is considered till 3 only since we have to reach the top. So this is out of the solution. We can't take this possibility. This is one answer again, and this will return 1. One way is there. So basically, if we see from this point, if we see from second stair at this point, we have only one way. We are summing up the ways coming from both the sides, but since this right one is returning 0, so we have just one way. Now this will return 1 upwards, and this also returned 1, so this path returns 2, as the answer. Going along this right path again, here again we can either take one step or we can take two steps. If we take one step, we reach the top. If we take two steps, we reach 4, which is out of bounds. So this path returns 1, this path returns 1 again. So we were getting 2 from the left side and 1 from the right side. So 2 plus 1 equal to 3. Now if you observe carefully, the paths that we are getting answer from is 1, 1, 1 and 1, like 3 steps, 1, 1 and 1. So this is this answer that we discussed earlier. The other answer that we are getting is 1 and 2. This is this path that we discussed. And the third answer that we are getting is 2 and 1. So this is this path that we discussed. So all in all, what we get to know is the answer for any particular point, starting from any particular point, will be the sum of answers that we get if we take one step at each point or we take two steps at each point. Whatever answers we are getting from these two, which are successful answers, which is getting us to the top, those are the answers which we have to sum up to actually find a final answer. So now we can try to write the recursive function for this, basically the recursive statement which will help us write the code. So for any generic point where we are standing, for any generic value of n, our answer will be the sum of the number of paths we are finding from by taking one step. So it's like if you're standing at 0, it's the summation of number of paths coming from 1 after taking one step and number of paths coming from the second step after taking two steps. So f of 1 is f of n plus 1 plus f of n plus 2. That's our recursive solution. Also, before moving on to the code, let's also discuss what the base case for the solution would be. So the base case would be I equal to n. So n is our target. It's the point where we have to reach at the end. So if we are already standing at n, if we're already standing at stair 3, that's when we've already got a successful solution. You would have seen that whenever we were reaching 3 in our recursive function, which means we would have achieved our target, we were returning 1 as the answer. So whenever I equal to n, that's one way that we've achieved. So whenever we come to this base case, we will return 1. Also, if we reach to a number which is greater than n, so if we reach 4, let's say, so that's an invalid path. In those scenarios, we will return 0. So now let's write the code for this problem. So we have climb stairs int n. I will just create a helper function. So int answer equal to helper, and we will pass on n. We will also pass on the starting point, which is I. Here it's 0. And at the end, we will return our answer. Let's quickly define our helper function. So as I told, the base case is if I equal to n, we have to return 1, and if I goes out of bounds, we can simply return 0. And the generic solution for any value of n would be a summation of number of ways that come after taking one step plus the number of ways that come after taking two steps. So if it's f of n plus 1 plus f of n plus 2. So I'll simply write return helper. I'll just write n I plus 1 plus helper of n I plus 2. We can quickly test our code and see if it works. Yeah, so you see that for 2 it's giving the answer as 2 and for 3 it's giving the answer as 3. Let's try to submit our solution and see if it works fine for all the test cases. So it's giving us a time limit exceeded result. That's because if you're making recursive calls, if you're making 2 calls at every step, the time complexity will be really huge, and it will go approximately 2 to the power n, because at every step we are making 2 branches. So it will, like, the branches will be 1 plus 2 plus 4 and so on, and it will come out to be 2 to the power n. So this isn't an optimal solution, and we need to make it better, and so that it works for higher n values. Since we're already given in the question time constraints, which is 45, and 2 to the power 45 is going to be very huge. So if we observe our recursion tree, we have a few overlapping subproblems. So you see 2 here, right? 2, again, here it has 2 parts and it's returning 1 as an answer. Here again we are having 2 and it's returning the same answer. So these are overlapping subproblems, and the substructure also is optimal here, and in such cases we can try to apply DP. So as we talked earlier that there are, in the previous video, that there are 2 ways of applying DP. One is memoization and one is tabulation. So memoization is quite easy to implement. What we can simply do is, instead of calculating the result for this stage or any particular value of I again and again, we can just memoize it. We can store the result in a DP table and we can refer to it. So before calculating it once again, we can always refer to it. If it's already stored, we don't need to calculate it. So let's say when we were going through this path, the left path, and we already calculated an answer for 2. So what we can do is, in our table, like let's have our DP table till from 0 to 3. In our table, we can store answer for 2 as 1. So when we again come to 2, in the right path, we already have the answer stored and we don't have to calculate it again. So when I'm coming to 2, I won't make any other recursive calls. I'll just check that my answer is stored in the DP table and I'll refer to the same answer and put it and just return the answer from here. So how exactly do we go about filling this DP table? Initially our DP table will be empty. So it will have -1 at all 4 places. Whenever we encounter any value of I, we'll check, is the value present at this I value, is the value for the DP table -1? If it's -1, then we have to calculate and we will update the value in the DP table. Okay, and if it's not -1, we'll simply reuse the value that we calculated earlier. So I'll just make the change in the previous code only. Let's make a DP table. I'll create a vector. Size will be n plus 1 because we have size 4 from 0 to 3. And I initialize it with 1. Vector int, let's call it DP. Now I'll pass on this DP table to our helper function for calculation. Okay, so I'll just take this in our helper function, and these base cases are fine, they'll remain the same. So if DP of I is not equal to -1, so as I said, if it was already calculated, we would have it stored in the DP table. So if it was calculated, we can simply return DP of I instead of going and making both of these recursive calls of helper I plus 1 and helper I plus 2. But it was not calculated. If the DP at ith index is still -1, then we'll calculate the result, store it in a variable, and we'll assign it to our DP. So the next time any call comes for the same value, we can just reuse it, right? So let's just run this and see how it works out. Okay, so we have a small error. Let's just pass on the DP table here as well. Okay, so we have to return from this function. So what we'll do is we'll return dpi. Now let's try and submit. So this got accepted. And why it got accepted is because the time complexity is significantly reduced when we memoize this solution. So how is the time complexity reduced is that we are always calculating ones for every I value. So when we came here at 2, we calculated for it once. But when we came at this 2 again, we didn't calculate. We just returned from our already stored answer in the DP table. So here, since we are doing the calculation once for every number, so the time complexity will be O of n. And the space complexity will also be O of n, because we are using a extra vector of size n plus 1. So this is a significant optimization over the recursive solution. Now let's also write tabulation solution for the same problem. So for the sake of tabulation solution, let's consider that, I'm trying to formulate the solution in a different way, similar, but just let's consider a different way. This was the ground and this was n. So we can also say that for reaching this n point, a person would come either by taking one step or by taking two steps. So a person can come either from the n minus 1th stair or the n minus 2th stair, n minus 2nd. So answer for n would be f of n minus 1 plus f of n minus 2. So the valid ways that are there to reach n from the n minus 1th step, and the valid ways that are there to reach from the n minus 2th step. That is the answer for f of n. It's very similar, it's just a different way of writing this. Initially we were having f of I equal to I plus 1 plus I plus 2, and it just makes same sense here. So we will try to write a DP solution for the same. For this particular approach, our base cases would be, first would be n equal to 0. So we're already standing at n equal to 0, and the answer would be 0 for this particular point. So there are no ways to, we're already at 0, so we can simply return 0 for n equal to 0. For n equal to 1, there is only one way to reach 1. So n equal to 1 means we can simply return 1. We can just take one step from 0 and we will reach n equal to 1. For n equal to 2, we already discussed earlier that there are two ways. Either we take two steps and we reach 2, or we take one step of 2 length. So either we take two steps or we take one step of 2 length. So the answer for 2 will be 2. So I'll write the code for tabulation, and we'll make a separate helper function for it. Okay, let's just make helper 1, or let's maybe write the code here itself in this function instead of making a helper function. That would also work. So we already have a DP table. We can fill up DP of 0 with 0. We can fill up DP of 1 with 1, and we can fill up DP of 2 with 2. These are the base cases that we already discussed. For the other cases, we'll just put a for loop. We'll start from I equal to 3. We have to go till n value, and we can do a I plus plus. So here dp of I would be equal to dp of I minus 1 plus dp of I minus 2. And at the end, we can just return dp of n. That's the desired answer, the number of ways there are to reach n. Let's quickly run this code. Yeah, let's submit it. So it's giving error, it's giving runtime error. That's because when n will be 1, we should not fill up dp of 2 value, because it will be out of bounds. So if in case n is equal to let's say 0 or 1 or 2, we can also simply write a statement. If n is less than equal to 2, we can return n. Now it should work. Yeah, so it got accepted, and this is the tabulation solution. So for this particular problem, we discussed the recursive solution, which was of complexity 2 to the power n and which was quite inefficient. We discussed the memoization solution, which was O of n in space and time complexity. So even the tabulation solution, which is a for loop, which has a for loop of length n, the time complexity will be O of n here. And the space complexity will be O of n as well, because we are making a vector of size n. So these were the 3 solutions for this problem. Now let's move on to the next problem. So let's discuss the problem, minimum cost climbing stairs. So we're given this problem on lead code, and it says, you're given an integer array cost where the cost I is the cost of ith step on a staircase. So there's a staircase, and it's the cost for climbing every step of the staircase is given. Once you pay the cost, you can climb either 1 or 2 steps. And so let's say we have, let's consider the first example. We have 3 stairs, and the cost of climbing them is 10, 15 and 20. So it's 10, 15 and 20. Now they say that we can start from the 0th index or the first index. So essentially the index 0 is this one. We can either start from this stair or we can start from this stair. And we have to reach the top of the staircase, the top of the floor. So we have to climb all the stairs and reach here. So here we have to return the minimum cost to reach the top of the floor. So as it is said, so there are 2 things. Either we can start from 0th or we can start from first. One is this, and then we can either take 1 step every time we climb or we can take 2 steps every time we climb. But irrespective of that, the cost of climbing that stair or starting from that stair will be the same, that is the value present at that index. So if I start from 10, I can either go to this stair or I can go to this. The cost will be 10 only. Right, so what I can do is, let's see what all ways are there and how much cost it will take. If I start from 10 and if I take 1 step, it will cost me 10. Then I start from 15 and I take 1 step, it will cost me 15. And then I again go to the top of the floor from 20, the cost will become 45. The other way is, so starting from 10, taking 2 steps will be 10 because the cost is same irrespective of the number of steps you're taking. Or and then after reaching here, the cost will be 20 again. So it will be 30. Another way is, so we started from 10, right? There was another thing in the question that we can start from index 0 or index 1. So now let's start from 15. So if we start from 15, I take 1 step, the cost will be 15. From 20 again, I take another step, the cost will be 20. The cost is 35. Or if I start from 15 and take 2 steps directly, the cost will be 15 only. Out of all these possibilities, the minimum cost comes out to be 15. So that's supposed to be our answer. So I hope the problem statement is clear. 2 things are there, either take 1 step or take 2 steps. And for starting, you can either start from index 0 or start from index 1. And we have to reach to the top of the floor and we have to find the minimum cost to reach there. So that's the explanation of this problem, and now let's try to figure out a solution for the same. So as we did in the previous problem, this will also have a recursion chart, a recursion tree. So for the recursion tree, we have 2 things. We have either we can start from 0th index or we can start from first index, and the answer would be the minimum cost that will come from both of these paths. So either we start from the 0th index or we start with the first index. The value at 0 index is 10, the value at first index is 15. Going down both these paths, so here at every index we can either take one step or we can take two steps. If we go one step down from 0, we reach 1, and if we go two steps down from 0, we reach 2. So when we go again from 1, we either take one step, we reach 2, or we take two steps, we reach 3. Then again, 3 is one of our solutions. 3 is like we've reached the top of the floor, so this is one valid solution and we can calculate the cost of it. So here it will like we've reached one of the base cases. 3 is the base case since we have to reach index 3. So it will return the values up top. So this will return, let's say at 3 there's no cost, so this will return 0, and here 1 will have taken the cost of 15, so 15 here and 10 here. So this particular path has the cost of 15 plus 10, 25. Now continuing over the other paths, after 2 we can take one step and go to 3, and this is our one of the goal again, like this is the top of the floor again, so this is one of the path. And if we take two steps, we reach 4, which is out of the bounds, so this is a discarded solution. And if we check a path that we've reached again, this is reaching from 2 to 3 and 1 to 2, and here's 0 to 1, so it's 10 plus 15 plus 20, so it's 45. So another cost we have gotten is 45. Since this is the minimum, so we've got two answers when we started from 0. One is 45 and one is 25. So the answer is like the minimum here till here is 25. We've yet to explore other paths, but the gist is that we'll keep exploring the recursive paths and we'll find the minimum that comes from either of the sides. So even if we go on 2 again and we find one answer, that will come out to be, let's just quickly make this recursion chart complete. So from 2 we can go to 3. We can go to 3, which is our final answer, or from 2 we can go to 4, which doesn't make sense, taking 2 steps. So this is discarded, and this gave us a cost of 20 plus 10, which is 30. And if we start on this path, so we took a cost of 15 starting from 1. We can either go to 2 or we can go to 3. This is one path and this returns a cost of 15. From 2 again we'll calculate the cost, but the minimum cost will be this one only. So this is how the recursion tree for this problem would look like. So let's write a generic recursive equation for a generic I value. For any particular I that we are at, we are looking at what if, what's the number of steps, what's the minimum cost, what's the cost that incurred if we take one step, and what is the one that's incurred when we take 2 steps. So either we start with 1 step or with 2 steps, but at the end we take the minimum of both. So our equation will have the minimum of whatever we get after moving 1 steps and whatever we get after we move 2 steps, plus we will also be adding the cost at that particular position, because that's the cost that's required to take 1 steps or 2 steps. So this is the generic equation. We can also write it in just the opposite way. So to reach at any point n, so let's say these are our stairs. So to reach this point, either we'll have to come from 1 step lower or we'll have to come from 2 steps lower. So the answer will be minimum of f of n minus 1 comma f of n minus 2 plus cost of n. because that's the cost that it will take to move from n. But keep in mind, this is for any generic value of I. But the final answer will be always the minimum of f of n minus 1 and f of n minus 2, because these are the two places where we can reach the top the top floor. So our goal is to reach to the top floor, and the answer for n will be minimum of n minus f of n minus 1 and minimum of f of n minus 2, because there is no cost to go from the top floor to anywhere. The top floor is already our answer. So this cost of n factor will not be there in the last like when we are considering for n. But for all other generic values, the answer would be f of n minus 1 plus f of n minimum of f of n minus 1 and f of n minus 2, and we'll be adding the cost of n. So our base case here will be n equal to 0 and n equal to 1, and for n equal to 0, the cost would be cost of 0. That's the value present at the 0th index of the array. And for n equal to 1, the answer would again be cost of 1, that would be given in the cost array. So moving on to the code, if n equal to 0, first just quickly let's write the helper function and get the value of cost dot size into n. So let's just say n equal to cost dot size. We have to calculate the minimum cost. I'll just get this get the answer from a helper function and store it in answer variable. So I will call the helper, I will pass on the cost, I will pass on n, I will pass on the I value we are on. So we have to calculate two answers. To reach n, we either come from n minus 1 or we come from n minus 2. So here, instead of calling it for one value, I'll call it for two values. I'll call it for n minus 1, I'll call it for n minus 2, and I'll take the minimum of both of them. And we already discussed that for n, the answer would be the minimum of n minus 1 and n minus 2, and the cost factor wouldn't be there because it's 0. So cost n, and I'll pass on n minus 1. I'll take the minimum of two calls. So minimum of helper, this, and cost n minus 2, and we'll return this answer. Now let's quickly write the helper function. The helper function is taking this cost vector. It's taking n, which is the size of the cost vector, and it's taking the value I, the generic value that would be. Now, as the base cases we discussed were n equal to 0, where the answer would be cost of 0, and if n equal to 1, the answer would be cost of 1. For the rest of the cases, we can return cost of I plus helper of I minus 1, that is, we'll be passing on cost n and I minus 1, and we'll have to take, as we discussed, we'll have to take minimum of two calls, one for the I minus 1th value and one from the I minus 2th value if a person is coming after taking two steps. Yeah, so adding cost of I, the current cost, plus the minimum of one step or two steps, whatever is there, and we can run this code. Before that, here we have to write I equal to 0. Here we have to write I equal to 1. So if we are finding the answer for 0th, it will simply be the cost present at the 0th index, and for 1 it will be the one present at the first index. So we'll just run the code now. Yeah, it is accepted, and let me try and submit the code. Yeah, so it works for most of the test cases, but it's giving time limit exceeded in certain other ones, and we know the reason for that, as we discussed earlier, that we're passing repetitive calls for certain values. So we can optimize this like we did in the last problem. We can first memoize it. So as you see in this problem, that there were certain repeating cases, like 2 was present here as well and here as well, and there are overlapping subproblems in this question. So like we did in the previous problem, so whenever we found a value for any index, we stored it in a memoization table, in a DP table, and whenever we come again to that value, we first check that if the answer was calculated for this particular index, and if it was calculated, we just reuse the answer. So like the previous problem, we'll just initialize our DP with -1, and as in when we calculate the answer, we'll store it in the DP table, and while calculating it again, we can just refer to the old answer. So I'll quickly memoize our already written code. Let's create a DP table. It will have a size of n plus 1. Let me initialize it with -1, and I'll pass this on in our helper function calls. We'll pass it by reference, and before calculating the value for any particular I, I'll check if dp of I is not equal to -1, which means if it's already been calculated, we'll just return dp of I. And if it's not been calculated yet, if it is equal to -1, then we'll calculate the value, we'll store it in the DP table, and then we'll return it. So let's just say I'll store it in this answer. I'll populate the DP table answer, and I'll return the DP of I. So let's see if this runs well. Okay, we have a quick error, so let's just pass on the DP parameter here as well. So it got accepted, and let's submit the code. Yeah, so it got accepted, and the time limit exceeded is not coming again because the time complexity is significantly optimized. Like the last problem, we'll see here that whenever we are encountering a same value, we're not calculating the answer again, and we are storing it in the DP table. So the repetitive calls are saved, and for every value we are calculating it only once. So the time complexity of this solution is O of n, and the space complexity is also O of n because we are maintaining a DP table of size n. Cool. So now let's move to the tabulation solution for the same problem. So instead of making another helper function, I will just write my for loop here itself. I'll comment the existing code. I will write a for loop. Before that, I'll initialize this DP table for our base cases. So as we always do. So DP of 0 is the cost of 0, and DP of 1 is cost 1. Now we'll write a for loop. Less than equal to n. So we actually don't need to calculate it till n because at the end we need to return the minimum of dp of n minus 1 and dp of n minus 2 because those are the two places that we can reach n from. So we'll calculate the dp till n minus 1, and at the end we can return the minimum of dp of n minus 1 and dp of n minus 2. So I'll just write the formula for dp here. We had minimum of dpi minus 1 comma dpi minus 2 plus cost of I. And at the end, instead of returning this answer variable, I will be returning minimum of dp of n minus 1 comma dp of n minus 2. I'll run this solution. Yeah, it's accepted. I will submit this. So it's accepted here as well. So this is a tabulation solution. The code looks a lot simpler than the recursive and memoization solutions. And here also the time complexity is O of n because we are using a for loop to iterate over n values, and the space complexity is O of n as well because we are maintaining a separate array of size n. So right now we saw three approaches. One was recursion, where our time complexity was approx 2 to the power n, and our space complexity was it was not any external memory that we were using, but the recursion stack was taking the space. And for the memoization solution, our time complexity was O of n and our space complexity was also O of n. For the tabulation solution, again the time complexity was O of n and the space complexity was O of n as well. This was also O of 2 to the power n. Now we can further optimize the space complexity to go from O of n to O of 1. How we can do that is, if you observe, our recursive equation is f of n. This is coming out to be f of n minus 1. We are taking the minimum of f of n minus 1, f of n minus 2, and we are adding the cost of n. So if we carefully observe, the value for any particular state, the value for any particular I, is depending on the previous value, the value for the previous state and next to the previous state. So it's just depending on two previous states. So what if instead of storing the values for the complete DP table, if we go by the tabulation solution when we are making a for loop, what if we store just the previous two values, because those are the only ones that will be useful for us. So we'll be storing previous one and previous two only, like the previous one and the next to the previous one. So let's say our answer for any particular array was 0 and 1 till two values. So the next answer is, let's say, the minimum of these two. So we'll store the next answer here and then we'll discard this one. We don't need this one because for the next one we just need this and we need to compare both of them to find the final answer. So we'll be storing just two previous values. So let's try and write this in code. So instead of maintaining a DP table, I'll remove this. Okay, so I'll maintain two variables. One is previous one, the other is previous two. And I will just okay, let's just name this previous one because this previous two because this is next to the previous one, and this is previous one, the immediate previous one for so here then again the cost, the DP for 0 and 1 is fixed. For 0 we have the answer as cost of 0 and for 1 we have the answer as cost of 1. So now we'll start from value 2. So previous 1 to value 2 is the answer that will be present for the value 1. So essentially the answer for value 0 was 0 and the answer for index 1 was 1. So for 2 we have, if we are coming on index 2, we have two previous values, the index 1 and the index 0. So previous 1 will be corresponding to index 1 and previous 2 will be corresponding to index 0. So now to calculate it for all the other values, we will just calculate the current answer for this index. That will be minimum of previous one, the previous value, and next to previous value, and then we will be adding the cost of I. Now we will have to update the previous values. So as I showed here, we will have to discard this value. So earlier this was previous one. This was 0 index, 1 index, 2 index. So then previous of 2 was this one index previous one, and this was previous 2, and current value we have calculated. So for 3, this will become previous 1. So previous 1 will become cur, and this will become previous 2. So previous 2 has to become previous 1. So we are just moving one value forward to update the previous for the next index. So we will just write previous 2 equal to previous 1, and then we will update previous 1 equal to cur. And then this will go on, and at the end we'll have updated previous 1 and previous 2, and we'll have reached n minus 1. So let's say this was the complete array of length 3. So these are the two values, like this would have become previous 2 and this would have become previous 1 after the updation. After we update in our line number 21 and 22, the previous 1 and previous 2 would have updated, and if we want to find the answer for n, we just have to look at previous 1 and previous 2 and take the minimum of both, because it's, you know, the previous answer and the next to the previous answer. So to return the answer, we can just say previous 1, previous 2. I'll run the code. Yeah, it's accepted. I'll try to submit it. And yeah, it works. So in this solution, we optimized the space complexity even further and made it as O of 1. So now let's discuss the next problem of the DP series, which is house robber. So this is a problem on LeetCode as well. It's a medium level problem. So let's say you're a professional robber planning to rob houses along a street. Each house has a certain amount of money stashed, and the only constraint stopping you from robbing each of them is that the adjacent houses have security systems connected, and it will automatically contact the police if 2 adjacent houses were broken into on the same night. So the constraint you have is that you cannot rob 2 adjacent houses, because it will alert the security system. So in this question, you have to make sure that no 2 adjacent houses are robbed together. So to further show the amount of money and to further provide the amount of money, they've given an integer array nums, and that represents the amount of money of each house. So you have to return the maximum amount of money that you can rob without alerting the police. Without alerting means you cannot rob 2 adjacent houses. So let's say, let's take the examples that are given in the question. We have the array as 1, 2, 3 and 1. So there are 4 houses, and the money that the houses have is 1, 2, 3 and 1 respectively. So here you can rob 1 and 3, the answer would be 4. You can rob 1 and 1, the answer would be 2. You can rob 2 and 1, the answer would be 3. So the maximum amount of money you can rob is 4 without alerting the police. So essentially, if it is broken down into simpler terms, you just have to find the maximum sum from the array, and you cannot take any 2 adjacent numbers, right? So maximum sum of a subsequence of array where adjacent numbers aren't included. Taking the next example as well and trying to find the answer for it. So we have 2, 7, 9, 3 and 1. So here our answer will come out to be 2 plus 9 plus 1. Because if we take any other combination, it's going to be definitely smaller than that. You can try and verify. So the answer here is going to be 12. So these are quite small examples and can be solved manually, but moving on to the bigger examples, we can try solving it using code. So that this will be a simple, this will also be a simple recursive solution as we've been doing. So we can start a recursion tree. So like, what is the constraint here? Once we rob one house, we cannot rob the next house. That's the only thing that we have to keep in mind. So when we start formulating our solution, let's say we are at index 0, okay. So either we can include the index 0 and we can put a constraint that we cannot include the index 1, right. So if we include the index 0, our answer is 1 up till now, and then we can pass on the index 2 because we cannot pass on the index 1. So for I equal to 0, we'll pass on the index 2 if we are including I equal to 1, and if we are not including it, then we can just pass on the index I plus 1 because we can have the best answer. It's possible to include I equal to 1, it's possible to not include I equal to 1, but from our end we are saying that we haven't included index 0, so now any answer that comes, whether we include 1 or whether we don't include 1, that will be a best answer, but we can start from index 1. We have that freedom. It's not restricted. So if we are passing on index equal to 1, the answer is still 0 since we haven't included the house at index 0. So the recursive calls will go like including a specific index and skipping the next index, or not including the current index and then we can skip the next index or we can take it. So we only pass the next index. So the recursive relation for this particular problem will be, one call will be to include the current index, and that will be f of I plus 1, and while taking the value at the nums of I, like including this house, and if we exclude this, it will be f of, sorry, if it will be in the first case, since we are including I, we won't be including I plus 1, and it will be f of I plus 2 plus nums of I, and for excluding it will be f of I plus 1, and we will be taking the maximum of both of these because we have to return the maximum amount that can be robbed. So whatever possibility returns the maximum amount, that will be our answer. We can
We can
also
also
write
write
this
this
in
in
the
the
exact
exact
opposite
opposite
manner.
manner.
So
So
for our complete answer for any particular index, let's say we are standing at index I, the answer for index I would be include index I, skip this one, and get the answer of I minus 2. So it will be f of I minus 2 plus nums of I in the include query, and if we are excluding I, then we will take the answer of I minus 1. Whatever answer is still here, that will be our answer. So whatever answer has come till I minus 1, whether it includes I minus 1 index, whether it doesn't include I minus 1 index, it doesn't matter because we are allowed to include that. So we will just take the answer that has come till the previous index. So when we are excluding I, the query will be f of I minus 1. So the maximum of these will be our answer. So either ways we can write. I am going to be writing the code using the second one. And talking about the base case in this particular solution. So for I equal to 0, when I equal to 0, the only house that a person can rob is house number 0. So the answer would be nums of 0. And for I less than 0, so let's say we are subtracting 2 from the previous index or 1 from the previous index. If in any case we reach a value where it's less than 0, then there will be no houses before 0, right? So the answer we have to return is 0 at that point because there can be no cost that is possible. So if there is no house, so there is no money to rob. So for I less than 0, the answer will be 0. So we'll have to return 0. So we can write the recursive code for this quickly. So we have n equal to nums dot size. I'll quickly create a helper function to help us calculate our answer. So our answer will be helper, and we'll pass on nums. We'll actually pass on n minus 1 because we have to calculate the answer till n minus 1. So whatever is the answer at the last index, since we are checking at every index whether to include it or not, so whatever is the answer till the last index, till the end of the array, that will be the maximum cost. So we have to calculate the answer for index n minus 1. We can return the answer. I will write the helper function. So it will take our vector nums, it will take the index. So if our index is less than 0, As we already discussed, if our index is less than 0, then we can return 0 because there is no houses before 0. If our index is equal to 0, then we can return nums of 0. Only one house is there, and that's the answer. Else, for the generic case, we can either include the current index and the value added. We can include it in our final answer, and then we'll have to go 2 indexes back, or we can exclude it and we have to go 1 index back. So I'll be writing the include query. That will be helper of nums. We'll be passing n minus 2 and we'll be including nums of n in our answer, the current index. And if we exclude this, we'll be passing n minus 1 and we won't be including anything. So that's simply nums of n minus 1. And then we'll be returning the maximum of both of these. So at every index we have two choices, right? Either to include the current index or to exclude the current index. Our answer is the maximum of both of these possibilities. So at the end we are returning the maximum of it. Let me run this code. Yeah. Try and submit this. So we are getting a time limit exceeded error due to a lot of recursive calls and a lot of repetitive calculations. So as we did in the previous questions, we'll again do the memoization solution for this one, because there will be possibilities that when we are coming one step back or two step backs from any particular index, there will be possibilities that we land on the same index multiple number of times. And when we are landing at the same index, we are calculating our answer again and again by the recursive calls. So what if we cache the answers for each of these indexes, like we did in the previous questions? What if we maintain a DP table, and whenever we find an answer, we store it in the DP table? So whenever it occurs that again we have to calculate the answer for that index, we can just reuse our previously calculated answer. So I'll just memoize this solution. I'll create a DP table of size n, and I'll initialize it with -1. I'll pass it on in our helper function query. And I will also take this one here, int. Have to pass it in the calls. Now initially the DP table has values of -1 for all the indexes. If we encounter an index where the DP of I is not equal to -1, which means we've already calculated the answer and stored it in the DP table. In that case, we'll return the DP of I. In other cases where it's still -1, we'll populate DPI to be the maximum of include and exclude query. We'll populate it with our answer and we'll return it. So since we're populating, the next time anybody tries to reuse, the answer will be available in the DP table. So we can run this. Okay, so actually we're using n as the index here. We'll run this again. TP of n, and yeah, it's accepted. Let's submit this and see if the TLE is still coming. Yeah, it's accepted, and the TLE is gone because we significantly optimized the recursive solution, and now we are calculating once for every value. So now again our time complexity becomes O of n, coming from O of 2 to the power n, where we were making an inclusive call, we were making an inclusive call and an exclusive call. So we were making two calls at every step and trying to calculate the answer. So from 2 to the power n, we have reduced it to O of n. And for the space complexity as well, since we are using a helper array and a DP array, so we are also using the space complexity of O of n here. So now let's also write the tabulation solution for the same. So in the tabulation solution, the other things are going to be same. This base case is going to be same. The recursive relation we're going to be using is going to be the same. We're just using a for loop to formulate the solution here. So our DP table is here. Let me comment out the code for the memoization solution. I'll just initialize our DP for our base case, which is DP of 0, that is nums of 0. We'll start calculating the answer for I equal to 1, I less than n, I plus plus. Now our answer will be int inclusive. So there will be two queries again like the previous one. In the inclusive one, we'll be adding nums of I plus we'll be adding dp of I minus 2. And in the excluded query, we'll be not adding the current value because we're not including it, and we'll be taking dp of I minus 1. And the answer for dp of I will be the maximum of inclusive and exclusive. At the end, we'll have to return dp of n minus 1, the answer till the last index. One small thing here is that for I equal to 1, I minus 2 will not be there, like it will be out of bounds. So we can just put a condition: if I minus 2 is greater than equal to 0, then only we have to take dp I minus 2, otherwise we can take 0. Because if it goes out of bounds, it's anyway there's no house present, so we'll take 0 here. So I'll just use this ternary operator here, and I think we should be good to go. Let's run the code. Let's put this in brackets. Yeah, so it's accepted. Now we can submit the code and check if it works. Yeah, so it works. So this was the tabulation solution of this question. Now, one thing that we've done in the previous question is that we noticed that our answer was depending on only two previous states, previous one and previous two. If you notice in this question also, our answer is depending only on two states, I minus 1 and I minus 2. So like we did the space optimization in the previous question, wherein we declared two variables, previous one and previous two, instead of making a DP array and storing the answers for all the values. In this question also, that space optimization can be done. That's what is your homework. You have to do the space optimization and try to make the space complexity to be O of 1. It will be very similar to the previous question, so it will be very easy to do that. So I hope you were able to understand how dynamic programming problems are solved using top-down and bottom-up approaches. If this video was helpful for you, make sure to like it. Make sure to mention any comments or any doubts you have in the comment section, and we'll be happy to answer. Subscribe to Scalar's YouTube channel for more such informative content. See you!